And we'll go from current slide. I may even turn on the projector. And I do have, that's coming up, this announcement. I made it last time, but for those who weren't here, just to let you know. Now, I don't know if any of you are ever planning or would ever come by on a Tuesday or a Thursday. That's when I have more office hours. I do have office hours between 8 and 8:30 on Mondays and Wednesdays, and you can catch me then, either in my office or up here. But other than that, I don't have any more office hours until 5:30 to 6. Okay, so I'm in class basically from 8:30 to 5:25 with only 2 little 5-minute breaks. So my biggest chunks of office hours, this is Reginald, right? Biggest chunks of office hours are Tuesdays and Thursdays between 10:45 and 4:30. Okay. Not tomorrow. Okay, tomorrow I have cataract surgery in my left eye, and we got word yesterday I'm to be there at 5:30 in the morning. Okay, so I will not be on campus at all tomorrow, because once they do the surgery, I'm supposed to sort of lay low for most of the rest of the day, so I'm not supposed to get out, certainly not drive or anything like that. So I will not be on campus at all tomorrow. So spread it around. If you know any of the classmates that aren't here, let them know not to come by tomorrow. Okay. After this, I don't know of any others. I do know sometime later this month I have a Tuesday morning doctor's appointment. That won't. I'll be on campus after that. Oh wait, I'll take that back. The follow-up visit for my eye surgery is going to be the following Tuesday. It had been scheduled for the following Friday, which is when I'm not on campus anyway. We don't, campus is closed, but the doctor's going to be out of town, so they moved it to Tuesday. But it's right across the street here, so I will be over there. I can't remember the times now. I think it's early afternoon, so I'll just go over there, have the visit, and come right back. So I won't be gone for very long. But and then later in the month, there's a Tuesday morning doctor's visit with hematologist, so that's something different. But I'll be back as soon as that's over as well. All right, any questions? Anything we've covered so far? Okay, we're in Chapter 2, Differentiation, 2.3, the product and quotient rules, and higher order derivatives. But before we go too much with that, did everyone get the first test? Anyone not get a copy of the first test? Okay, good. All right, so we're on page 123, example 1. We had just talked about the product rule. Here we're going to do the product rule. Find the derivative of h of x. Okay? Now there's actually 2 ways to do this problem, maybe more than 2. 2 ways that would be pretty straightforward. One way would be multiply it out. Those are just 2 binomials, multiply them out by FOILing, and then take a derivative. That would certainly be legitimate. However, they want us to practice the product rule, so let's do the product rule. How does that go? Let me get my pen set up. Come on. Okay, I think my computer's tired this morning. Slow moving. Okay, here we go. So what is h prime of x? By the product rule, how does that go? And now this is going to start doing that again. I don't know why. Where do we begin? What does the product rule tell us? Anyone remember? It was a long time ago. Monday, okay. How does the product rule go? Well, let's see. Here's basically, well, that's a little more complicated. Here it is, right here. Take the derivative of a product of 2 functions, which is exactly what we have there, product of 2 binomials. It's the first times the derivative of the second, plus the second times the derivative of the first. That's it, okay? First times the derivative, and does the order matter? No, you could say derivative of the first times the second. You could do that one first, and then vice versa. You can do it any order you want to, because addition and multiplication are commutative. You've just got to get the terms in there in the right place. Jeremiah is here. Does anyone else come in since or call it off? I don't think so. Okay. So, What is h prime? How would you begin? Okay, the first, 3x minus 2x squared times 4. That's all, folks. Okay, what's next? Plus, what's next? Okay, you can do the derivative of the first, which is 3. A little louder? Minus 4x, is that what I heard? Okay, not only is my eye bad, my hearing's bad, okay? Times 5 plus 4x. Okay. Now, to get a reason, that is the answer, okay? But it's not very clear looking. It can be simplified significantly. So let's do that. Let's first distribute the 4 across, and what would that give us? Distribute the 4. 12x minus 8x squared. Now this is going to require some foiling, okay? That's a plus sign, so I'll go on and put the plus. Okay, we'll do the first, and that's 15. The outer minus 12x. The inner oh, you're right, plus 12x. Inner minus 20x. And then finally the last, minus 16x squared. All right. That looks a lot worse, doesn't it? Okay? But we can combine a bunch of like terms. Now, I would normally start with the squared terms, the quadratic terms, but those are both negative, so let me start with something that's positive. The x terms are going to be, well, let's start with the constant. That's just one of those, and that's 15, right? Okay, so that's taken care of. Now let's do the linear terms. It'll come back. And what does that give us? 12 and 12 are pretty easy. 24 minus 20 plus 4x, and then we got our negative ones minus, help me, minus somebody? 24x squared. All right. Here's Jasmine. All right. Anyone else come in since the public? Okay. Certainly a reasonable seeming answer. Let's do it the other way just to check. This problem I find would be easier to just multiply it first and then take a derivative. Let's see if it works. That way we'll confirm, hey, do we have it right? So let's start by foiling the h of x. H of x is equal to (15x) plus 12x squared, right? Enter, minus 10x squared, and then finally the last, minus 8x cubed. Sorry, it's running out of room here. Hold on just a minute and let me mark Jalen, if I can find them. I know you're in here. There you are. Good. Anyone else come in since it's called off? Okay. Now let's take the derivative of that. Oh, let's combine like terms. What will that be? 15x doesn't have a like term. plus 2x squared next minus 8x cubed. All right, now let's take the derivative of that. H prime of x, pretty simple here. What would that be? Get out of there. Okay, 15 plus 4x minus 24x squared. Ding, ding, ding. It matches, doesn't it? Well, when it comes back on, it does. Yeah, perfect match. Okay, so it doesn't matter which way you do it. The derivative is still the derivative. Okay, as long as you do it right. Now, frankly, with a problem like this, I'm much more likely to make an error in the product rule than I would be multiplying first and taking derivative straightforwardly. Okay, so I would tend to go this way. But they wanted us to practice on the product rule, and probably just one that would be easy, real easy to tell what the derivative is the other way, and sure enough, they are exactly the same. Any questions? Now notice, you don't have to do. In the book, it says the first times the root of the second plus the second times the root of the first. You don't have to do it that way, just like you did. The root of the first times the second. Fine, it doesn't matter. Multiplication is commutative, addition is commutative. You can do the second first and first second. It doesn't matter, okay? As long as you get all those pieces in place somewhere, okay? All right, any questions on that? Minus 24x squared plus 4x plus 15. They like to do it in descending order. I like to lead off with a positive. It doesn't matter. All right, let's see how they do it then, if it's anything significantly different. Any questions before I erase it? Everybody got it? Okay. So they do the first times the root of the second. You can write it in this way if you want to. Don't worry, they're going to quit writing it in this way after a while. Plus the second times the root of the first. But again, you could have done this over here, this over there. You could have flipped these two, flipped those two. It doesn't matter as long as you have all the pieces in place, somewhere in place. Okay? So what we did, 3x minus 2x squared times the derivative of that was just 4. That's that one. And then they put the second first, 5 plus 4x times the derivative of the second, which is 3 minus 4x. Everybody see that? Again, which order you do it doesn't really matter as long as you do it all. Okay? Now you just have to distribute and see what you get. 12 minus 8x squared plus 15, and they did it all at once, which is I tend to do as well. 15 from here, and from here you get a minus 20x and a plus 12x. It's a minus 8x, and then a minus 16x squared. Okay? Then you can just remove the parentheses and combine like terms, and that gives you minus 24x squared when you combine those two, plus 4x when you combine those two, plus 15 when you combine those. All right. Any questions? Does it make sense? All right. No mystery meat here, right? Please, if anything does seem fuzzy or misty or uncertain, ask. Please ask. We got time, we'll take time. Everybody got it? Just about. Okay. right, they're skipping examples 2 and 3. So let's do example 2. They did the real easy one on the slide set. This one's a little more involved, but not much. Y is equal to 3x squared times sine x. How would you proceed? Find the derivative. I'm going to write y prime. You can write it any way you want to. What would be the derivative? How would you proceed? Help me. Say again? 6x. Okay, going to start with the derivative of that. That's perfectly fine. 6x times what? Okay, it's the derivative times the other, not derivative times derivative. Okay, the product rule says that first times derivative of the second plus second times derivative of the first. It doesn't matter which order you do, but you never multiply derivatives together. You multiply a function times the derivative times the function, however you do. So 6x was okay to start. That's the derivative. So what do you write down here? Sine x, okay? And then you do the plus 3x squared times cosine x. Okay, excellent. Okay. Now that to me is a perfectly fine answer. If you wanted to factor out what you could, you don't have to. You could get a 3x out of both of those. So you could have 3x times 2 sine x plus x cosine x. There's no reason to do that. No better, no worse. It's just if you don't like seeing common factors in there and you want to get them out, okay. They do that, okay. Of course, they did it in a different order, but it doesn't matter, okay. 3x times, they put the x cosine x first, plus 2 sine x, exactly the same answer. And again, if you're using WebAssign or one of those pre-programmed package homework management, whatever you call it, systems, if you didn't have it in that order, they were going to say it's a wrong answer, and it is not a wrong answer. That is a correct answer. Reversing the order here is a correct answer. Leaving it like that is a correct answer. All of those are correct answers. Okay? There's nothing wrong with reversing the order of those two or leaving it in that form. Absolutely nothing. All right. Any questions? Make sense? All right. Let's back up. Clear this one. All right, clear? Okay. All right. And we'll do example 3. Find the derivative of this one. Y is equal to, it'll come back, I hope. Okay, there it goes. 2x cosine x minus 2 sine x. Okay, so we're looking for y prime. I don't know why it's doing that, but it seems to do it. I write on the screen, it jiggles a little bit and it shuts it down, but it almost always comes back. So, how would you proceed with this one? The first term involves a product. The second term really is a product, but guess what? It's no variable in the product. That's just a constant times a function. So these are done slightly differently. How do you do the first term? How would you begin? Several ways to go. In fact, there's something I would be tempted to do at the very beginning, just because I'm pretty lazy. Is factor out the 2 rather than have to deal with them. But we can live with them. We'll do that at the end. So, how would you proceed? Get me started on that first term. Anybody? A little 2. That's a good start. Times cosine x. That's the derivative of the first times the second. That's fine. Then you follow that with a, okay, I put a plus, but I'm going to hold off of that for a moment because I know what's coming. Plus 2 what? x times negative sine x. That's why I went back and changed the plus to a minus. Minus 2x sine x. Does everybody see that? Product rule here. Okay, she did the derivative of the first times the second. And then it was really a plus the first times the derivative of the second. But since the derivative of the second is negative, that's why we put a minus sign there. Okay? But we're not through. What's next? What's next? Second, minus 2 something, derivative of sine, cosine x. Okay. Now what you see happens. The 2 cosine x and minus 2 cosine x add to 0, so your y prime here just happens to be minus 2 x sine x. Surprise, surprise. Okay? Let's see how they did. That's what they got in the book too. Good for them. Any questions? Happens to be first term from your, or one of the terms from your product rule happens to cancel the derivative of the second term. You won't find that happening too much, but it can. There's nothing to prevent it. Any questions? Is it making sense? No mystery meat here. Mystery might be why, but that's another question. Everybody got it? Oh no, it's still right. Okay. Everybody got it? Okay. Now let's move to the quotient rule. Okay, regular derivatives, not too bad. Product rule, a little more complicated, but not too bad. Quotient rule kind of stinks, okay? It's a lot more involved. The quotient, f divided by g, as long as f and g are both differentiable functions, okay, with two differentiable functions, f and g, is itself differentiable at all values for x for which g of x is not equal to 0. Because if g of x is equal to 0, that function doesn't make any sense. That function is not defined, so you sure can't take a derivative there, okay? Not where x equals 0, it's where g of x equals 0, because that's in your denominator. Moreover, the derivative f divided by g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. Isn't that easy to remember? Okay? Now, and here's expressed one way. Derivative of a quotient of two functions, f divided by g, is start with the denominator, g of x times the derivative of the first. Now this one, things do matter. This is not a plus here. So you can't reverse the order and just put signs anywhere you want to. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared, as long as that denominator is not 0. Because this doesn't make sense, it's that 0, and of course that wouldn't make sense either. Now, I'm going to pick on the Indian accent again. Is that okay? All right. I think I told you before I was tutoring our good Indian friend's son. We're good friends with them too. And he had been studying in India, and when he came back, and when he said the quotient rule, here's how it came out. And it's great. I love it. low d high minus high d low over low low. Okay? Okay? Again, low, the denominator, d high, derivative of the numerator, minus high, d low, over low low. Low times low. And ever since then, I've remembered it. But he said it much faster. Low d high, minus high d low, I can't even say it. My tongue won't go that fast, okay? But that's a good way. Start low, and okay? Low d high minus high d low over low low. I've not found an easier way to remember that, okay? That may not make any sense to you, but I found it interesting, okay? So let's find the derivative of this one, okay? They do a little proof in the book, and again, if any of your math majors, and I know the one math major I know about, he's at a camp, I believe he said today, so he wasn't going to be here. Okay, so how do we take the derivative of this y prime? How would you begin? Get out of there. Don't show us how to begin. Let me just tell you this again if I didn't tell you before. If you do see this start strobing or fading in and out and stuff like that, point it out to me. It could be the projector. It's done that before on its own. But it could also be my feed from the computer, because this plug-in here sometimes doesn't make good contact, and if it starts wiggling and jiggling, I may be running on batteries and not realize it, and that'll make it fade some. So let me know if you see that. Okay? So, where would you begin? Okay, yeah, here's your low, x squared plus 1 times 5, that's d high, minus 5x minus 2 what's next? Times, so again, a little louder, 2x, is that what I heard? 2x, great, over low, x squared plus 1 squared, if the two will show up. Okay. My screen is strobing a little bit on me, but this one doesn't seem to be, so I have to check and make sure I've still got connection. All right, there are some things we can do to simplify this, especially the numerator. What would that be? Let's distribute. Oh, wait, somebody came in. Saw you, but I was checking your mouse. Okay. The mirror here, right? Okay. Let's find you in here. All right, good. Anyone else come in since Paul was talking? Okay. So let's simplify that numerator. What would you do? Distribute. 5x squared plus 5 minus 10x squared second. Watch those signs. Minus times minus is plus 4x. Is that what you said? Okay, all divided by. I would not multiply that denominator out. Leave it as x squared plus x plus 1 squared. There's no reason to. It's not going to usually simplify anything. Just leave it like that. But you can do something to the numerator. What's that? Combine like terms. And again, I don't like leading off with a minus sign, so I would write it as 5 plus 4x minus 5x squared. There's no real reason for that. I just don't like leading off with a minus sign. Over x squared plus 1 squared. Doesn't look all that simplified to me, okay? But that's as simple as we can get it. Now, if you had opportunity to, see if that would factor, see if you can factor it, to see if you can eliminate a common term. But guess what? Even if you factor that, the best you're going to come up with is a first-degree polynomial. This, when you factor it, is going to be a second degree. There's no way that's going to eliminate common factors. So therefore, don't mess with it. I mean, this is just as good a form as any. If it is factorable in the numerator, you could factor it if you wanted to, but it's not going to help you simplify. Okay? And I know that Ryan came in. Okay. Anyone else come in since I called up? Okay. So right now we're only missing Patrick, who told me he would be out, Joy, and Devin. Okay. All right. Any questions on this? Everybody got it? Well, you'll see it again. The book's going to do it. They may do it slightly different order, but it should be pretty close to the same. Let's see what they do. By and large, it should be the same. All right. They start just like you started. Low, D high, there's the D high, minus high, D low, over low low. The product, the square of the denominator. Okay? And then they actually do that and got the same thing you did at one step. They took two. That's fine. Take as many steps as you need to see what's going on. X squared plus 1 times 5, that's the root of the second of the numerator, minus the denominator, the numerator, 5x minus 2 times the root of the denominator. The root of that is 2x, and over this. And then they did it this way, it's fine. They multiplied these two together, and then minus multiplying these two together. Now they're going to distribute the minus sign across. Perfectly fine. In fact, that may help you from making a mistake. If it does, do it that way, okay? Do anything you can to help from making a mistake, and then they leave out steps and tell you the answer. Same answer we got, I just let off with the positive 5 plus 4x minus 5x squared. It doesn't matter the order you write that answer, unless you're checking it on WebAssign, and then they'll tell you that's wrong. And it's not wrong. Perfectly legitimate answer. All right. Any questions? Got it? No questions? Okay, that was example 4. They're skipping examples 5 and 6. So let's go back and do 5 and 6. All right. Example 5. Very different sounding problem. Find an equation of the tangent line to the graph of f of x is equal to, oh boy, what a fun function, 3 minus 1 over x over, get out of there, over x plus 5, okay, at the point negative 1, 1. And what we're looking for is an equation of the tangent line. Okay, that's what we're looking for. Now, first thing, I'm a cynic, okay? I don't want to launch into and do a whole bunch of work and find out the problem didn't make any sense. So I first want to make sure the problem makes sense. Is 1, 1 even on this curve? Negative 1, 1. How could you tell? Plug in a minus 1 for the x, and that would give you 1 over minus x. 1 over minus 1 would be, okay, it would be 1 over minus 1 would be a minus 1, and minus would make it a positive 1. So 3 plus 1 is 4, divided by minus 1 plus 5 is 4, and that gives you 1. Yes, that point is on the curve. Okay, so I'm okay with that now. But now what we've got to do, How can we find the equation of a tangent line? What do we need? Say again? We need a slope. How do we find the slope? Take a derivative. You got it. Okay? So the first thing we need to do is f prime of x. Now you don't plug in the minus 1 first. Take a derivative of that, you get 0 because you would have a number then. You have to do it with the x's in there. So how would that go? You tell me. How do you start? Anybody? Help me. Anyone? Derivative? Second? Derivative of what? I can't hear it. Yeah, that's what we're trying to do. Derivative of f of x, yes. How do we start that? What kind of function is f of x? A quotient. So we use the what rule? Quotient rule. And how does that go? It starts what? Okay, yeah. Though usually it does start with that. Usually say low d high. Okay. So just to keep my little song in place, let's do the low, which is x plus 5 times the derivative of the numerator. So you're right, derivative of the numerator is here. What's the derivative of 3? 0. Okay, we got that part. What's the derivative of minus 1 over x? Okay, so let me go off to the side. We were trying to find d by dx, and I don't want to write it as negative 1 over x. I want to write it as negative. How do you write that? I don't like the variables in the denominator. So how do I write it? X to the negative 1. Perfect. What's the derivative of that? Minus 1 times minus 1, which is plus x to the negative 2. So this would be 1 over x squared. Okay? Now I went back to that form. Now that's just the first one. That's the low d high. What comes next? What? Minus okay, it's high d low, right? Okay, high is 3 minus 1 over x. And what's the derivative of the denominator? D low. Second? 1. Okay, I can handle that one. So there's my numerator. Low d high minus high d low over what? A little louder. X plus 5 squared. Perfect. Perfect. Now that numerator is kind of a mess. Why? You got variables in the denominator. Okay? So I'll take more time than I usually do on it, but probably still not enough time. That first one you could write is this, x plus 5 over x squared, right? Minus, now let's do this in parentheses, not a bad idea, okay? I'm going to come over here and do a little chicken scratching. Make that 3 over 1, right? That's 3, right? No difference there. Now, of that term there, what's our least common denominator? X. Okay? Now, how to get an x in the denominator here, you would have to, of the 3, you would have to multiply numerator and denominator by x, right? Because 3x over x is still 3, right? Okay? So you got 3x minus 1 over x. 3x minus 1 over x. Okay? All this is over x plus 5 squared. Okay. Now, you got another case of not the same denominators. What is it going to take to make those two denominators the same? Make the second one squared, so you have to multiply this by x, meaning you multiply this by x as well. Okay? So this is going to be x plus 5. Now I'm going to do my numerator. All this is over x squared, right? Okay? Now I'm going to multiply that and negate it at the same time. So this will be a minus 3x squared, right? And this will be a minus times a minus, which is plus x. Was that too much of a shell game? Do I need to go back and explain? This is Joy. All right. Now we're only missing Patrick, who said he would be out, and Devin, who didn't say he would be out, but I know this last Thursday he had to be out too. I know he has to take care of a sister some days, and it has to be today. All right. Does that need any explanation, or are you following what we did there? Got it? Okay. So what do we do next? We almost are there. F prime of x is equal to combine like terms. And again, I don't like leading with a minus sign, so I'm going to put 5 plus 2x minus 3x squared divided by x squared. Oh, I forgot. All this is over x plus 5 squared, right? Get back here. All right. So this is over x plus 5 squared. All right. Now, there's our f prime. That's not what they were asking for, though, is it? They were asking for the equation of a tangent line. All this does is give us our first derivative. Why did we do that anyway? Oh, we need to find the slope. Where? At minus 1, 1. So how do we find the slope if this is your first derivative? Say again? You may have said it right, I just can't hear it. Plug in a negative 1, that's exactly right. So we want to know what f prime of minus 1 is. Okay? Start plugging, folks. I'm going to erase some slide. Is that okay? Because I just have very limited room here. So it's all right to erase this? I'm doing it anyway. I don't care. No, I'm sorry. I didn't say that, did I? Not out loud. Okay. So what's f prime of minus 1? Well, I can start with the 5. That doesn't change. Next. Minus 2. Yes. Okay, next. Second. Minus 3. Right? I can stop right there. That's going to be my numerator. And what does that add to? 0. Okay? Whatever I do to that denominator, the numerator is still going to be 0. Well, it's a good idea to check and make sure it doesn't become 0. No, that'll become a 1 there. That will become a 16 there. So that's going to be 1 times 16 is 16. Doesn't matter. This derivative is 0. Okay? Now, if the derivative is 0, what does that tell you about that tangent line? If the slope is 0, what does that tell you about the tangent line? It's horizontal. Okay? And where does that horizontal line go? Picture over here on your graph. Horizontal lines could be anywhere here. All of those are horizontal lines. What do you know about this particular horizontal line? What point does it have to go through? negative 1, 1. So the horizontal line that goes through y is equal to 1 is right there. So there it is. That is your equation of that line is y is equal to 1. So horizontal line is going to come back. Okay. The horizontal line, there is no x variation in it. The x is, no matter what the x is, y is always 1. Okay? That almost seems like it's not fair to give you one that easy, doesn't it? But they did. Okay? And they went through a lot of effort to get there, but that's exactly what they got. Now, they went to the effort of graphing it. And I know some of you don't have your text, so you can't see the graph. And poor folks at home, you should be here. No, Patrick, sorry. Okay, I know you can't be. But you got the book. I know I saw you with the book. So, here's the graph. Now that, all right, I don't know if I can hold on too long. Obviously, x can't equal 0, or else that wouldn't make sense. And x can't equal a negative 5, so that doesn't make any sense. So you have at the y-axis, x equals 0 and x equals negative 5. And then the function does all sorts of funky stuff other places. But we're interested in that point right there. It happens to come down here, and that happens to be the tangent line right there. Okay? So, I didn't want to graph that, and I don't really have a lot of room to graph it, so hopefully that will do for you. Any questions? If you need to see it graphed, I'll be glad to graph it, sort of. I won't mind graphing it too much. Okay. Any questions? All right. Let me, I meant to say this at the very beginning, I forgot to. And I haven't even noticed, so I may be preaching to the choir here. But I think I mentioned this on Monday too, but if in case I didn't, let me say it again. Sometime into the term, and we're well into the term now, usually the administration comes out and says, we're removing all unpaid students from the roll, okay? I can't tell you when that's going to be because it just seems when anyone takes a fancy to do so, okay? So let me just say this, in case any of you haven't completed your payment yet, please get that done so you don't get removed, and then you usually can figure out a way to get back into the class, but it's a bunch of administrative hassle. See if you can get that completed and done before they do that, because I have no clue when they do it. They just, whenever they take a fancy. There was one summer they did it, they would have already done it by now. Last summer or summer before, and other summers they just let it ride for a while. You can't ever tell, so please, if you haven't completed payment, at least let the business office know what your plans are, and then they may keep from removing you, if that fits. I know one of them, it's a small class, all 6 people are paid, so I don't have to announce that to them. A very small class. All right, any questions? That was example 5. Okay, let's go to example 6. I will try to go to example 6. Are you listening? The computer isn't doing anything. Ah, there it goes. All right. There we go. Example 6. Now. Oh. I didn't do example 5 the way the book did, and it worked. Let me go back and show you how the book did it. Sorry about that. I wish I hadn't erased it now. Here's what they did. F of x is equal to 3 minus 1 over x over x plus 5. We did it straight with the quotient rule, and it worked. It was a little messy, admittedly, when you got to that 1 over x here. But let me show you what the book did, which is a little bit, I think, neater and cleaner. Okay? This form right here, they sometimes, some math books will call a complex fraction. I understand what they mean by that, but a lot of times in math, when we talk about complex, you get that concept of a negative, square root of -1 in there. This is not that kind of complex. So I'll call it a complicated fraction, but other people say, well, all fractions are complicated. No, this is a little more complicated because you have a denominator here, but a denominator up here as well. And back when you were in algebra, sometime in your long-distance past, how you simplified that was find that least common denominator of all the denominators in the numerator and the denominator, and you only got one, which is x. Multiply the numerator by x and the denominator by x. Now, why is that legal? What is x over x? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value at all. Okay? Now, the only time you can't is if x were 0. You can't then divide by x. But if x were 0, your whole problem doesn't make sense. So x can't be 0 to begin with, so it doesn't hurt to divide by x. Okay? So when we do that, what the numerator becomes is x times 3 would be 3x, and x times minus 1 over x, that would just be a minus 1, because the x's would cancel out, right? Then your denominator gets a little messier, x times x plus 5. And since we're going to do derivatives, probably makes sense to go on and multiply that out. X squared plus 5x. Okay. And then they did the quotient rule from that, which was a little simpler. Okay. So you pay up front, and it makes it a little simpler later, or not do the extra up front and a little more complicated later. Either way works. This way will still give you the answer. If you got a text, you can look at that and see how it works. It comes out exactly the same. It's better. All right. Sorry I didn't notice that. Or I would have said something as we were going. Okay. Now, I'm going to erase this again before we move to example 6. Example 6. Now, these are just some little hints to make things a little easier to do, okay? It almost seems completely out of place here, but it sort of makes sense here. What if you had this as a problem? Y is equal to x squared plus 3x over 6. Would you use a quotient rule on that? You could, but what happens when you do the derivative of the denominator? It's a 0. So then a lot of your stuff falls apart, and it's so much easier not to do that. Okay? Here's what they suggest you do first. Factor out the 6. Make it 1 over 6 times x squared plus 3x. Now they don't even think about a quotient rule. This is just a constant times a function, that numerator, okay? And take the derivative of that, what would you do? Second? Not a product rule, you don't even need that. This is just a constant multiple. It's just 2 times 1/6, that'd be 1/3 times x, plus 3 times 1/6 is 1/2. Because that x goes away. One step, you got it. Take a derivative of this. Now, if you wanted to, you could do this. If it helps you see it better, distribute that across and make it 1/6 x squared plus 1/2 x. Now you're not even tempted to use a product rule, are you? You take a derivative of this, and the y prime would be goodness, this is blinking like crazy on me. 1/3 x plus 1/2. And there's your derivative. Now, if you went back and did your denominators, in fact, if you did, well, you get the same thing either way. One way you could do this is just 1/6 times 2x plus 3. That's probably the simplest way to write your answer. If you factored out a 1/6 here, you would get a 2x plus 3. So, to me, this is the simplest way to write the answer. These are both absolutely correct answers. Absolutely. There's no difference. If you distribute this across, you get that. Okay? But guess what? WebAssign is probably only going to take one of those or some other answer and tell you everything else is wrong. It's not. Those are right. Okay? Second? Yeah, okay. That's okay. What you're saying here is 2y prime is equal to 2x plus 3 over 6. Absolutely. Is that what you were meaning? Absolutely. That's another absolutely correct answer. In fact, according to the book, that's the one WebAssign would say was right, and it would say those two are wrong. They're not wrong, they're absolutely correct. But yeah, that's what you get. So there's no reason to do a quotient rule or even a product rule with it, because that's just a constant multiple. You see, if you pull this out like we did here, take the derivative of that, then just put the denominator back in, you got it. Same thing. Okay? Absolutely correct. Okay? So many different ways to do these. Quotient rule would work. It's just extra work for no extra value. Product rule will work. Just extra work for no extra value. Simpler to do it this way. Okay, let's do the B one here. Y is equal to 5x4 over 8. Quotient rule? No, avoid quotient rule at all possible. Product rule? Not really. How would you rewrite that first? 5/8 times x to the 4th. And then it's just 5/8 times the derivative of x to the 4th. And what's the derivative of x to the 4th? What's the derivative of x to the 4th? Second, 4x cubed. Right? Okay. 4 will go into 8 twice, so this is going to be 5/2 x cubed. Or if you want to write it back like it was to begin with, 5x cubed over 2. If you want to write it back in that form. And this time they left it in this form. So they're really inconsistent with which way they do it, but either of those is perfectly correct. And you could probably think of another correct way to do it. 2.5x cubed, that would work, okay? There's lots of ways to write that answer absolutely correctly. Make sense? Okay. This is just saying don't use a complicated rule if there's an easier way to do it. In other words, I've told you this, haven't I? What makes a good mathematician? One feature, one characteristic. Gotta be just a little bit lazy, right? Always trying to find the simplest way to do a problem. Okay? Any of you qualify? No, you're all, oh, got a couple of lazy people. The rest of you hard workers, you can do it too. There's no penalty for being a hard worker. Okay. How about this one? Y, this is a little more complicated. Y is equal to minus 3 times 3x minus 2x squared over 7x. What you think? That one obviously looks like a quotient rule, right? Or wrong? What you think? Second, product rule, did I hear? Okay. What would you say? Be lazy, simplify first, then see what you get. Now, what is one thing you know you can do to this term? You can multiply through. You could. Or what's another thing? Second? Factor out an x. It has a common x in it, doesn't it? So rather than multiply through, factor something out. Okay? And that will be, you'll have a minus 3, and when you factor the x out, that'll be a minus 3x. And what's left over? 3 minus 2x. And this is divided by 7x. And what can you do now? Divide out the x's. Okay. Now, time out for a moment here. One thing you have to keep in mind, if you're going to graph this or do something else with it, x cannot be 0. Even though when we get it in that form, it looks like there's no problem with it, in the original form, x cannot be 0. So in this form, it still can't be 0, but this becomes minus 3/7, factor out that too, times 3 minus 2x. And if you were going to take a derivative of that, y prime would be what? Minus 3/7. You got to hang on to that. And what's the derivative of the inside? Say again? Did I hear a negative 2? Yes, I thought I did. Times negative 2. And that is simply, that's an ugly 2. There it comes. So this is going to be 6/7. Negative 2 times negative 3 is positive 6 over 7. That's it. That is it. Quotient rule would work after a lot of work. Who wants to do that much work? Not me. Okay? Simplify as much as you can before you differentiate. All right. Let's do the D one. I don't think it's going to fit on here, so I'm going to erase it. All right, to erase, it's still writing. All right, everybody got it? So let's erase that and do the D one. Okay. Y is equal to 9 over 5x squared. How would you approach that if you're trying to take a derivative of it? Brute force, quotient rule, or what? How would you write it? 9 over 5 times second? You could do 1 over x squared, but then I'd say how could you rewrite that? X to the minus 2, because I far prefer things in exponential notation rather than rational notation. If you can get away with it, exponential notation works. Now, how would you take the derivative of that? Y prime would be negative 2 times 9/5, which would be minus 18/5. What next? X to the negative 3. You got it. Now, if you wanted to write it back in rational notation, you could rewrite that as minus 18, if I could write. This pen is hanging up on me. Okay. And not, let me clean it up some. Okay. It's sort of like it's dragging. Okay. Minus 18 over 5x cubed. If you want to rewrite it so it looks more like your original problem, that's how you do it. You don't have to. That answer is perfectly good. And probably several other answers are good, but that's the way they did it. they put the minus sign in front here rather than up to the 18. That is correct too. Okay? Lots of different ways to write it. No way is most of the time any better than the other. They wrote it as minus 18 over 5x cubed. Okay. Which is good, but that answer is just as good. WebAssign may not think so, but it is. Okay. That finishes example 6. Any questions on example 6? We've still got example 7 to go before we get to the next subtopic. Okay? I forgot to take out my watch, I think. How are we doing on time? Okay. I think we can go a little bit longer before a break, don't you? Or do you? All right. Let's do example 7. All right to erase? Okay. Example 7. Now, we're going to expand a little. No, we're not. This is something we've already been doing. In fact, we just did it. It's the power rule, but this time we're going to have negative integer exponents. Now, I've been imagining we already had those. I think we have, but if not, we're going to hit them now for the first time. I don't know. If n is a negative integer, then there is some positive integer, k, such that n is equal to minus k. So if n is less than 0, but an integer that's negative, then you can say there is a k such that n is equal to 1. Yuck. Wrote the 1 in the wrong place. Minus k. Okay? If n is a negative integer, then k is a positive integer you can write as minus k. Okay? It's a strange way to start, but it is. Okay? Now, why in the world would you want to do that by the quotient rule? Okay? I do not know. But they're saying d by dx of x to the n for the life of me, I see no reason to do what they're doing. It still works. What does the power rule tell you to do? Taking the derivative of a power. What do? It's the exponent, n, times x to the n minus 1. Just reduce by 1. So what if n is negative? It still works. We just did it on the last one that way. So I see no reason for this example except they're showing you that indeed it still works. Okay? But why in the world even mess with the quotient rule on that? I do not know. And then they say in exercise 73 in section 2.5, which is a couple sections off, you're going to show that it even works for rational numbers. Maybe we only did it for positive integers, but I've already been using it as if it works because it still does. Even if n is negative, it still works. So I'm not going to fiddle with that anymore. Let's move on then to derivatives of trigonometric functions. Okay? Now, we know 2 already, don't we? Yeah, sine and cosine. What's the derivative of sine? What's the derivative of cosine? Negative sine. You got them. Okay? Now, if you know those 2, the quotient rule will help you do the rest of them. Okay? Because if you know the derivatives of sine and cosine, you can use the quotient rule to find the derivatives of the four remaining trigonometric functions. Now, derivative of tangent. What in the world is tangent anyway? Sine over cosine. So let's do it by the quotient rule. Okay? D by dx of sine x over cosine. Remind me of how the quotient rule goes. Anybody? Is what? Cosine x, that's low. Cosine x times cosine x. Derivative of sine is cosine x. Okay, got it? Minus sine x high d low. What's the derivative of the denominator? Negative sine x. Okay? All over cosine squared, right? Got it? Okay. Now, this numerator right here is cosine x. Cosine times cosine is cosine squared x. And a minus times a minus is a plus sine squared x over cosine squared x. Well, what's sine squared x plus cosine squared x? 1, always. And what's 1 over cosine squared? Is secant squared x. There it is. Yeah, that works. Okay? And we could do the same thing with cotangent. It's just cosine over sine. You'd wind up with a minus cosecant squared x. You can do that on your own if you want to. Now this one's a bit squirrelier, okay? But it will still work, okay? You want to see it or you want to just take your word for it? Not too bad to do. What you think? Want to see it? You want to be convinced, okay? You're cynics, okay? So let me clear the screen here, and we'll do the secant. What is secant? D by dx of, what is secant? Help me somebody. What is secant in terms of sines and cosines? It's what? 1 over cosine. Okay. Now, I'm real tempted to write that as cosine to the minus 1. Now, that doesn't mean inverse cosine. That means 1 over cosine. Okay? Okay, this is where things get a little hairy here. Usually that means inverse cosine. So I guess maybe to keep from doing that confusion here, let me put this to the minus 1 out here. That'll be a little clearer. That can't be confused with inverse cosine. How do you take the derivative of that? Oh, we don't know how to do that yet, do we? Shut. Okay, we're going to have to use quotient rule, sorry. There is an easier way to do it, but we don't have that in our tool belt yet. Okay, so we're going to have to hold off on that. So let's do 1 over, I said it was going to be easy, but it still is. 1 over cosine x. Okay? By the quotient rule, which is a pain in the neck, what would that be? How does it go? Low, which is cosine x. D high, what's the derivative of 1? 0, so that goes away. Minus high, I can do that on 1 times d low. What's the derivative of cosine? Second, minus sine, so that would be just a sine x, okay? All over cosine squared. So I'm going to write this as cosine x times cosine x. Now there's a reason that I'm writing it that way. Okay? Because now I can rewrite that to be sine x over cosine x times 1 over cosine x. And what's sine x over cosine x? What's that? Tangent x, there it is. And what's 1 over cosine x? Secant x. So there it is. Derivative of secant x is secant x times tangent x. And similarly, if we did the same type thing with 1 over sine, you'd only be off by a sine, and it would be negative cosine x times cotangent x. Okay, now here's an interesting little feature, especially if I were to write this above here. D by dx of sine x is equal to what? You know that. What is it? Derivative of sine? Cosine. And if I write over here, d by dx of cosine x, it's what? Second? Minus sine x. Okay, you knew that from before. But here's an interesting little thing. The functions that don't have the cos in front, like sine, tangent, and secant, their derivatives are all positive. Okay? Those that do have the cos in it, cosine, cotangent, and cosecant, those are all negative. Now that's just a happenstance there, but it's something to help me remember, because one of the things that trips me up more often than anything else are those silly little minus signs. So this is how I remember the signs for the trig functions. If it doesn't have a co in the name, its derivative is positive. If it does have a co in the name, its derivative is negative. Then I have to remember what it is. Sine and cosine are really easy. Actually, tangent and cotangent are not bad either. Did secant and cosecant, once you get it down, it's not bad. Okay? Any questions? Now, let's do example 8. Goodness gracious, I hate it when they do this. Okay, there's your function. What is the derivative of y prime? Yep. 1, good. Minus, good. Second? Secant squared. Perfect, perfect, perfect. Way to go. Okay? How about that one? What's the derivative of y? Y prime. What would you need to do? What rule? Product rule, I thought I heard somebody say. And how does that go? Okay, x times, what's the derivative of secant? Derivative of secant. Just did it. Exciting stuff, wasn't it? Derivative of secant is? Help me, somebody. Dying up here. Having to hold my hand in place too long. Derivative of secant is? Secant tangent. Secant tangent. Okay, that's the first half. What's the second half? Let's say again. It's plus, okay, plus, okay, the secant times 1. So it's just secant x. Right? It's first times the derivative of the second plus the second times the derivative of the first, which is just 1. Okay? Now, they may write one line below it, do they? Yeah. Oh, and then they also do this. No reason, but they do. They factor it out of secant x out of both sides, and that left an x, tangent x here, and a 1 there. Why they switch the order, I have no idea. Okay? Now, even something silly like that, if that's what Web of Science was looking for, but you had written it this way, they'd probably still tell you it's wrong, when it would absolutely be correct, okay? So that's one reason I don't really care for that too much. You probably haven't guessed that, have you? No, okay. All right, any questions? That's example 8. Example 9. This seems, okay, let's squeeze in example 9 first. Differentiate both forms of this. Then, let's see. Y is equal to 1 minus cosine x divided by sine x. But you could write that as 1 over sine x minus cosine x over sine x. Couldn't you? Yay or no? Sure could. Okay? Well, what's 1 over sine x? Cosecant x minus, and what's cosine over sine? Cotangent x. Okay? Now what they're asking me to do is take the difference in distance, which is 1 over pi 1. Closely. And take the difference in that, which is 1 over pi. On the surface, that seems like to be easy. Then you have to remember that you can always apply. Let's do the first rule first. So what would the y prime be? How does that go? How does it go? Help me somebody. Rho, which is sine x, times, y'all don't like my little phrases. I find it so much easier. Derivative of the numerator, derivative of 1 is 0, plus derivative of minus cosine. Positive sign. Okay? Okay, that's the first term. Second term is minus pi, which is 1 minus cosine x, below what's the derivative of the denominator? Cosine. Okay? All over, so split, right? Sine squared. Yeah, that's what I thought you said, okay. Sine squared x, right? Okay. Now, let's clean up that numerator a little bit, okay? Sine times sine is sine squared x minus a 1. No, I mean minus a cosine, because the 1 is multiplied by cosine. Minus cosine x, and then minus a minus is plus cosine squared x. All over sine squared x. Okay? Now, notice what we got in here. We got a sine squared x plus a cosine squared x. That's right. 1. Right? So we have 1 minus cosine x over sine squared x. 1 minus cosine x over sine squared x. Ooh, what a mess. So this looks like this becomes, get out of there, 1 over sine squared x minus a cosine x over sine x times 1 over sine x. I'm just running out of room, so I'm skipping a few steps here. Cosine over sine squared is cosine over sine x. What is 1 minus sine squared? 1 over sine squared. cosecant squared.
So if I try to, oh, maybe I can. This is CSC squared x minus, what's cosine over sine? Cotangent x, and 1 over sine, you just told me, cosecant.
Okay, there's our answer that way. Let's do it this way.
Derivative here, y prime here. What's the derivative of cosecant? Derivative of cosecant.
Hint, it's got a co in it.
Huh? Got negative. Okay, and then what's the derivative of the cosecant? Cosecant cotangent. CSC x COT. Okay, there's the first part. Minus a cotangent. Cotangent has a co in it. So that's going to be a minus, which is going to be plus. What's the derivative of cotangent? Cosecant squared. CSC squared. Okay? And guess what? This is exactly that. This is exactly that.
Okay? Now, what does this tell me? I almost say it's not working. Oh, you don't have to work. Okay, let me just go back and apply. Like this. Okay. So and while we're there, and the derivative of cotangent is minus cosecant squared. So if you knew those, then this becomes this. This is tangential. Let's get through what otherwise I really love it. Now it's in the fourth grade. Like we say, there's time. So much fun. Really. Alright. Alright, so that was example 9. Bottom of page 127, we've gone over an hour and a half, right? Time for a bladder break, muscle break, get up and walk around break. Yay or no? I'm all in favor. So we'll pick up with this slide when we come back. Bottom of page 127, there's a summary below, shows that much of the work in obtaining a simplified form of derivative occurs after the differentiation. In fact, you'll hear me say this, especially, I think I say it even more in my later classes like Cal 2, maybe even Cal 3. The calculus turns out being the easy part. All the manipulations that go before the problem or after the problem, that usually is more complicated than the actual calculus part. But here, note that the two characteristics of a simplified form are the absence of negative exponents and combining like terms. And we've been doing both of those pretty reasonably. Now, so let me back off and say this. Excuse me. Okay? Excuse me. Before you take a derivative, I far prefer having negative exponents. In their answers, they usually don't like not to have the negative exponents, so I have no real problem with it. But example 1, if you solve, after you differentiate, you get this, okay? But then when you simplify it, there's actually more work done getting from here to here, or almost as much as it was doing the product rule, if you go back to example 1. Example 3, I don't know why they periodically have these vertical lines there, but they just show up. Let me make sure my computer was still getting power. When you differentiate, you have it's long, but it was pretty simple doing. And I think this was another product rule, but yeah, it was a product rule. But when you simplify, like this and this disappear, then you wind up with that. So in this case, the simplification was pretty easy. Quotient rule, when you differentiate, you get this. After simplify, again, distribute, combine like terms. That's most of it, okay? Here was another quotient rule problem, distribute, combine like terms. That's most of what's involved with it. And again here, multiply or distribute here and combine like terms. And the simplification make the answers a lot more reasonable. So don't leave them in these forms. It's really hard to tell whether you've made an error in that or not. Go and take them down to simplified form whenever you can. I really don't think that was worth a table and a slide, but they seem to think so. Now, if you notice, the title of this section is Product and Quotient Rules and Higher Order Derivatives. So we have been through 1, 2, 3, 4, 5, 6 pages of product and quotient rules, and 1 page we're going to do higher order derivatives, okay? But it's pretty simple. You just do the same thing over again. Just as you, if you remember, can obtain the velocity function by differentiating the position function, you can obtain the acceleration function by differentiating the velocity function, okay? You just do another derivative. Another way of looking at this is that you can obtain the acceleration by differentiating the position function twice, okay? So if you have s of t, that's your position function. ds dt is going to be your velocity function. And d2s, d2t, in other words, differentiate that again and differentiate the velocity function, that gives you the acceleration. Okay? Now, have we hit double primes? See, I'm teaching all 3 calculus classes Mondays and Wednesdays. I can't remember what we covered in one and what in the other. No. Have we hit multiple integral? I mean, no, is this the first time? Okay. So that's why it's coming up now. A function a of t is called the second derivative of your position function, denoted by s double prime. Okay? The second derivative is an example of a higher order derivative. You can define derivatives of any positive integer order. Okay? Third derivative, 17th derivative, whatever. Okay? By just taking the derivative of the previous derivative. So the third derivative is just taking a derivative of the second derivative, which is gotten by taking the derivative of the function to begin with. The first derivative, which was taken by taking. So you just keep taking derivatives of your derivatives, and that's what that means. There is another notation for it, and this may be a little clearer. Okay? There are many notations, okay? Y prime means taking the derivative of y. If y is equal to f of x, which it is, then take the derivative of f, okay? Or this y prime means dy dx, derivative of y with respect to x. Or d by dx of f of x. Derivative of f of x, you can put this up there. df of x dx, okay? Same deal. And then this one we haven't really used much. This is the derivative operator, which is this operator right here, d by dx, okay? That operator is capital D, and you just put what you're taking with respect to down there, and you're taking d by dx of your y right here, okay? Now, you could put the f in there if you wanted to. That would be reasonable as well. Second derivative. Now, here's where, well, they still don't quite write it as simply as they could, okay? Let me write it the way that, to me, makes, and it's nothing special, okay? Your first derivative is d by dx. If you're taking a derivative of that first derivative, you're doing d by dx of the first derivative, right? Because the first derivative, you started with y, and then you took d by dx of your y, right? Just like you did d by dx of the f. We'll do another d by dx. What does this look like it is? It looks like two d's in a row, which they call d squared y, and then you have two dx's in a row, which they call dx squared. Now, don't think this is d of x squared. No, it's dx squared. Okay, the dx is what's squared. The dx is an entity there, and that's what's squared. It's not really squared, it's just you're taking it of itself twice. So that's where this notation comes from. And this comes out of the second derivative, and this is d2 dx, okay, it's exactly d2y dx squared. d2 by dx squared of y, okay? And then over here it's your d by dx function squared. In other words, you take this d by dx and square it, you get d2 over dx squared, okay? And what is third derivative, fourth derivative, nth derivative. Oh, here's the deal. In the prime notation, they never do more than 3 primes. In fact, in 3 primes, sometimes it's really hard to see. How many kick marks are there? If you had 4 of them, 5 of them, after a while, it's hard to count. So after 3, they put it in parentheses. Okay? If that didn't have parentheses, that would be y to the 4th power. With the parentheses, that means the 4th derivative of y, 4th derivative of f. If you didn't have parentheses, that would be f to the 4th power. This is clear. That's d4 d4y dx4, or d4 by dx4 of f of x, or capital D sub x, 4th of y, or of f of x. And then anything higher, you put in parentheses, the nth derivative of y, the nth derivative of f of x, the nth derivative of y again, d ny of dxn, d to the n over dxn of f of x, or d sub x. All those mean the same thing. That's what we mean by higher order derivative. You just keep taking a derivative as many times as it says to you. Okay? Let's do the example. Example 10. Because the moon has no atmosphere, a falling object on the moon encounters absolutely no air resistance. In 1971, y'all don't remember it, do you? I was 20 years old then, okay? All right, okay. Astronaut David Scott demonstrated this, and can you imagine this on the surface of the Earth? If you held a hammer in this hand and a feather in this hand and dropped them, what would happen? Okay, the hammer would go down here and the feather would do this kind of thing. After a while, finally make it to the ground, right? Hammer, right? That's all because of air resistance of the feather. Hammer has a little bit, but negligible. Feather has a lot. Well, I think the picture in the book shows it. He actually did that. Well, you can't tell, but he did it. And when he dropped the hammer and the feather, believe it or not, they both went down in the same way. Okay? No air resistance, nothing opposed motion. Okay? Now, they went down more slowly than they did on Earth because the moon also has a small acceleration due to gravity, but still they fell out the same way. Okay? So, the position function for each of those falling objects was S of t. They just gave you this function, is minus 0.81 t squared plus 2. Okay, now if you're wondering where the plus 2 comes from, that's because he probably held them about like this. And I'm assuming it's less than 2 meters. Astronauts, I don't know if you realize this, astronauts are typically fairly short. Because to fit in these little capsules, you have to be a little bit short. Okay? So all people you won't see bring, well, you probably didn't know, but, you know, any professional basketball player as an astronaut. Not for a while, because they just don't fit. Okay. So, he probably held it up. That's where the 2 came from. Okay. Where S of t is the height in meters, okay, and t is the time in seconds. Now it says, what is the ratio of Earth's gravitational force to the moon's? Okay. That's a really strange sounding question. With all this, what's the ratio of the Earth's gravitational force to the moon's? You're supposed to be remembering this. S of t is equal to minus 1/2 g t squared plus v0 t plus s0. That's our basic equation that we had sometime in the past for movement, okay, for falling. So basically what they want you to do here is if you take a derivative of this one, now this g here is the g on the Earth, okay? If you take the derivative of this one, you get s prime of t is equal to 2 times 1/2, so it'd be minus gt, right? Plus v0. Okay? Take the second derivative of that, s double prime of t, and you just get minus g. That's the acceleration of gravity here on the surface of the Earth. Does anyone remember what that was? In meters in the SI system? 9.8. That would be meters per second squared. So let's do the same thing to this. Let's do s prime of t, and what would that be? Yeah, 2 times negative 0.81, that would be 2 times 1.62 t, right? The 2 disappears. It'll come back, okay. And then if you take the second derivative of t, this will be minus 1.62. So if so g on the moon would be 1.62. So take the ratio of those two, which does it say? Ratio of Earth's gravitational force to the moon. I don't like them saying force, acceleration due to gravity. That would be 9.8 divided by 1.62. See what kind of ratio that comes up being. Punch it in your calculator, see what you get. Or just reduce it. This would be 4.9 over 0.81. Whatever. What kind of number you get? Say again? 6.0 something another. 49 blah blah blah. So that's approximately 6 times. The Earth's acceleration due to gravity is about 6 times that of the moon's. That's why I said when they dropped them, they're not going to fall as rapidly, but they will still hit the ground at the same time. Okay. Make sense? They rounded it to 6.0. That was sort of a made-up kind of a problem, which is fine for them to do, I guess. But there were easier ways to do it. But that's what they wanted you to do. Homework exercises here. 2.3. Any of the odds, 5 through 9, they're all at Calc Chat. 5's at Calc View. Do any of the odds 11 through 15, they're all at Calc Chat. 11's at Calc View. Do any of the odds 17 to 21, they're all at Calc Chat. 21's at Calc View. Do any of the odds 23 to 27, they're all at Calc Chat, 23 is at Calc View. Do any of the odds 29 to 39, they're all at Calc Chat, none of them at Calc View. Do any of the odds 41 to 55, they're all at Calc Chat, 41's at Calc View. They say using technology, take derivatives of any of the odds, no, do 57. It should be at Calc Chat as well. You don't need technology, you can just do it. There's nothing prohibiting that. Okay, then do either 59 or 61, they're both at Calc Chat. Do any of the odds 63 to 67, they're all at Calc Chat. Either 69 or 71, they're both at Calc Chat. Any of the odds either 73 or 75, they're both at Calc Chat, 75's at Calc View. Try doing 77 and 79, they're both at Calc Chat, 81's at Calc Chat. And then you do any of the odds 83 through 89. They should all be at Calc Chat. Then you can do any of the odds 91, to 99. They're all at Calc Chat. 91's at Calc View. Do either 101 or 103. They're both at Calc Chat. 101's at Calc View. And do either 105 or 107. They're both at Calc Chat. You can do 109 if you're interested in following that up. 111 and or 113, they're all at Calc Chat. 115 is sketching a graph, that's at Calc Chat. You can do either 117 or 119. They're both at Calc Chat. 121 is a Calc Chat, 123 is a Calc Chat, 125 is a Calc Chat. You can do either 127 or 129, they're both a Calc Chat. And then some true false, 131 to 135, they should all be at Calc Chat. And there's a proof at 137 if you're interested in that. Any questions? That's a lot of homework exercises. You don't have to do them all, but do some of them. And the reason I go through these every time is, even if you don't have a book, you can go to Calc Chat and or Calc View and see the homework. Now, they're already worked out for you, but just at least see what the homework problems are. Forget about what the answer is, and then work them yourself, and then compare them with the answers. Without a book, you can still be doing the homework. Okay? So, here's their solution to example 10. I forgot they had it. To find the acceleration, differentiate the position function twice. Take the derivative once, and you get minus 162t. Second time, you get negative 1.62. That's your acceleration on the moon, which means the acceleration due to gravity on the moon is 1.62. Okay? Meters per second per second. Compare that with 9.8 meters per second on the Earth, and you get something awfully close to 6 times. Okay, exactly what we did. All right. Well, there we go. The system's a little slow. Let's move on to 2.4. Now, just looking ahead, folks, we got 2.5 and 2.6 to go, and then we'll be ready for our Chapter 2 test. Guess what that means? Yes, besides a woo-woo, that means I need your Chapter 1 test in before we get there, okay? I don't want you making the same mistakes on Chapter 2 test as you did, so get that into me, if possible, sometime next week. I don't think we'll quite be ready for this. I don't know. We could be. We're going to get started in 2.4 today, and Monday we'll probably do 2.4 and 2.5, and Wednesday 2.5 and 2.6. We may not be ready by Wednesday, but it will be awfully close. I may have it ready for you so you can have an extra weekend to work on it if you choose to. So let's do the slideshow from current slide. And we're still in the chapter on differentiation, Chapter 2. Chapter 2.4, we're going to do one of our favorites of all time, the chain rule. Any of you familiar with this already? Okay, this opens all sorts of doors. Remember when I said, oh, there's an easy way to do it? Oh, nope, we haven't done that yet. We'll have to do it the hard way. Chain rule can make some things much easier. All right, so what we're going to do is find the derivative of a composite function using the chain rule. Does anyone remember what a composite function is? It's a function of a function. So let's say that you have a function. Name me a function. Just make up a function. Second? Someone said something. Name a function. Maybe not those functions. Okay.
2x plus 5.
2x plus 5. There's a function. What if we're going to operate on that with a different function, like the squaring function? Then we're going to square a 2x plus 5. Okay? That's a composite function. Okay? That's a very simple one, but it is. Well, taking derivatives, we need to use a new process to do that. That's not a multiplication. It's not a division. It's another process, and that's called the chain rule. We'll find the derivative of a function using the general power rule. Okay? We've already introduced the power rule, and I think in the last section we extended that to negative exponents, which I had already done, not realizing we only dealt with positive before. But we'll do the general power rule. We'll simplify the derivative of a function using algebra, which I think we've been doing too. And we'll find the derivative of a trigonometric function using chain rule as well. And that's the one I said, there's an easier way to do this. Whoops, we haven't done that yet. Now we'll be able to do it. So, we have yet to discuss one of the most powerful differentiation rules. We talked about product rule, that's good. Quotient rule, sort of messy, but it's good. Chain rule, really good. Okay? This rule deals with the composite functions, adds a surprising versatility to rules discussed in the two previous sections. Okay? You'll be so surprised. Okay. For example, compare some functions below. This you can take the derivative without the chain rule. This one, no way. Okay? There you got a function inside another function. We don't know how to do this without the chain rule. Here we can take the derivative of sine x, but if you're taking the derivative of sine of 6x, wait a minute, the sine's a function, but 6x is also a function. We don't know how to do that. Easy to take the derivative of 3x plus 2, that would just be 3. But here we have that 3x plus 2 raised to a power. Okay? So that is a composite function. We don't know how to do that yet. This one we could do, that's the sum. Derivative of this plus the derivative of that, pretty easy. But derivative of this is still just as easy, but we can't do derivative of this. We can do derivative of the tangent, but not of the x squared, until we get the chain rule as part of our tools in our tool belt. Basically, the chain rule states that if y changes dy du times as fast as u, and that's basically what it is. This is the rate of change of y with respect to u. But u changes du dx times as fast as x. This means the change of u with respect to x. Then y changes, okay, du du times du dx times as fast as x. Okay? So this gets us from a function of another function to the variable. Okay? And this tells us how to do it. Now we haven't had it yet. They haven't said it. So let's, nope, not yet. A set of gears is constructed here, such that the second and the third gears are on the same axis. So here's gear 1, here's gear 2, here's gear 3, and there's gear 4. If you turn the crank here on gear 1, okay, you turn the crank several times here to get gear 2 to turn fairly slowly here, right? Whatever gear 2 is turning here, 3 is turning here. Okay? And then gear 3 turning gear 4 again, this turns it fairly slowly. Okay? Now, as the first axle revolves, that's this one, it drives the second axle, which then drives the third axle. Okay. Let y be, okay, y, u, and x represent the numbers of revolutions per minute of the first, that's y, of the second, that's u, okay, no, and x, which is the third axle. That's the RPMs, revolutions per minute, of the first, second, and third axles. Okay? Now what we want, and you know, this, when I look at this problem, I think they're doing it backwards, okay? Because they say find dy du, du dx, and dy dx, and show that this is indeed true, okay? So axle 1 is turning at so many revolutions per minute. It could be a big number or a small number, okay? U is the number of revolutions per minute of the second axle, okay? Now, just by looking at this one has to go faster to make this one turn even slowly, okay? But then as slow as this is turning, this one's going to turn even more slowly. So basically what it's saying is the rate of turn of this one times the rate of turn of that one gives us the rate of turn of that one. Okay? And that is indeed true. Say again?
Is that like rate of change? Not like rate of change, or
Is that like what?
rate of change?
Yeah, that's exactly what a derivative is a rate of change. The change of y with respect to x. The change of y with respect to u, the change of u with respect to x. Those are, each one of them, a rate of change, which is revolutions per minute. Well, no, that's not quite true, because these are all revolutions. Okay. So, here's example 1. Because the circumference of the second gear is 3 times that as the first. Now, I didn't catch that here. Yeah, okay, here we go. The radius of the first gear is 1. The second gear is 3. The third gear is 1. And the fourth gear is 2. Okay? Those are the radii. You just double that to get the diameters. Now what? And then the circumference is pi times the diameter. Okay, so they're just multiples of each other. Because the circumference of the second gear is 3 times that of the first. The first axle must make 3 revolutions to turn the second gear once. Okay? That's what we get here. Like I said, this has to turn 3 times to make this go around once. Because this has fewer teeth, this has more teeth, this has to turn a lot of times to get that to go. And that's a 3-to-1 ratio. Okay? 3 turns of axle 1 to get 1 turn of axle 2. And then 1 turn of axle 2 is only going to do half a turn of axle 3 because it's half. This is 1, that's 2, so the number of turns is twice as much. Okay? So, because the circumference of the second gear, 3 times that of the first axle must make 3 revolutions to turn the second axle once, but the second axle must make 2 revolutions to turn the third axle once. So, dy du, that's the change of y for change of first axle for change of second axle is 3-to-1. The turns of the second axle to the third axle is 2-to-1. And if you multiply that together, combining those two results, you know the first axle must make 6 revolutions to turn that third axle just 1 time. Because it's 3 times 2. Okay? So like you just said, it's a rate of change. So you can write The rate of change of y with respect to x. The rate of change of the first axle with respect to the third axle is the rate of change of first axle with respect to second times the rate of change of second to the third. Okay? Now, I'm going to show you something. And most mathematicians would slap my hand for saying this, okay? Because these are operators. But if you take a look at this, doesn't it look like you're canceling out the du's and winding up with dy over dx? That's not a bad way to look at it. It's not what you're doing, but in practice, that's what it comes out to be. So that should help you get your chain rule in the right order, you might say, because that certainly is what you have here. Okay. 3 times 2 will be 6. The first axle turns 6 times as fast as the third. Okay. The rate of change of first axle with respect to the third axle. Okay. Now, why this problem seems backwards to me, they put the handle on this one. So it seems like to me this should be the driving force, and you should be looking for that there, which is 1/6. This, you know. So it seems like to me we're working the problem backwards, but it exactly 1/6. But they're showing it this way, which is fine. There's nothing wrong. In other words, the rate of change of y with respect to x is the product of the rate of change of y with respect to u times the rate of change of u with respect to y. Okay. Why all that? Well, here's the chain rule. If y is some function of u, okay, and we want it to be a differentiable function, you can't take the derivative of u. It means it has to be continuous, but that's not all. I mean, it has to be smooth and continuous, okay? Now, u is g of x, so u is a function of x, and g is that function. That's a differential function of x. And that means it's smooth and continuous. Then, if y is g of f of x, since u was g of x, and y is f of u, then y is f of g of x. There's your composite function. Okay? If you wondered back in pre-calculus algebra why they ever came up with this, this is why. So you can understand what the chain rule is. Okay? So then dy dx, which is this variable, the change of y with respect to that variable down the road there, is the dy du times du dx. Okay? Or equivalently, the change of y with respect to x, change of your composite function with respect to x, is the change, the first derivative of the outer function, right here, f, okay, with respect to whatever that g of x is, okay, times the derivative of g with respect to x. There's the key, folks. It's the derivative of the, if you have a composite function, the derivative of the outer times the derivative of the inner. But the outer is evaluated at the inner function, not at the value of x. Okay. So when applying the chain rule, it's helpful to think of a composite function, f of g, as having 2 parts. The inner part is the g part, outer part is the f part. Okay? Just what I was saying. Okay? The inner function is that g of x equal u. Okay? So derivative of y is equal to f of u, that would be f prime evaluated at u times g prime evaluated at x. Okay? Derivative of the outer function at the inner function u times the derivative of the inner function, just du. Okay. All right. I guess they're just showing you how you do these. This is a composite function. It's a really simple composite function. One function is the 1 over x function. That's the outer function. 1 over u function, okay? And the u is x plus 1, okay? So to do this, and this is, we're not taking derivatives yet. This is so simple to do, we won't do this one yet. When they get a little more complicated, you have to focus in a little bit better. But this is just showing how the composite functions go together. The outer function is the reciprocal function, that one. The inner function is x plus 1. Okay? What is your outer function?
2x.
No, that's the inner function, 2x. Outer function is sine, exactly. So the inner function is 2x, the outer function is your sine. Okay? What's the outer function? The square root function. The inner function is that polynomial. There's the inner function, the polynomial. The outer function is the square root function. Make sense? What's on the outside? The square root side. Inside, that's what's under it. Okay? So you would take the derivative of the square root function and then times the derivative of the inner function. When we get there, we're not quite there yet. Okay, what's the inner function there? Tangent. What's the outer function? Inner function is tangent. Outer function is the squaring function. You're just squaring the tangent. Okay? Inner is a tangent. The outer is the squaring function. Is there an E? No. Okay. All right. What's that? We'll see. Okay. All right, they did do more than half a page of a proof of the chain rule. And back when I was in college, my professor went through every proof in gory detail. Maybe that's why I avoid them. But if not a bad idea to read through the proof here. That was example 2 we just saw. Let's do example 3. You asked for it, you got it. Toyota. Okay. Whoops. Let me get my pen back. They have all these wordy stuff at the beginning, slide after slide after slide. There was 10 slides without a single thing that you actually could do. Now we finally are going to do one. Okay, find dy dx for y is equal to x squared plus 1 cubed. Okay? Now again, there's 2 ways to do this problem. We could actually cube that function, okay, and then come back and take its derivative. That would be pretty straightforward, just really messy. Okay? Or we could use the chain rule. Okay, so what would dy dx be? Okay, well, what's the outer function here? The cubing, not cube root, the cubing function. Okay, and what's the derivative of a cubing function? 3 times whatever's inside, x squared plus 1 squared. Perfect, yeah. The cubing function, if this was a y, oh no, not a y, a g in here, it'd be 3g squared, right? Okay? You keep the inner, okay? But then you do what? Take the derivative of the inner. And you multiply it, and what's the derivative of the inner? 2x. You have it. Now, a little bit of cleaning up to do. There's always that. 2 times 3 is 6x times x squared plus 1 squared. Okay? That wasn't too bad, was it? Okay? So that's why the inner and outer functions are important. Now, again, since you're multiplying, it doesn't really matter. A lot of people I've seen do it. I just sort of am stuck in the mud the way I like to do it. But a lot of people will take the derivative of the inner function first, then take the derivative of the outer function. Doesn't matter. It's the same answer. Okay? But I see folks doing that a lot. As long as you keep it straight, that when you take the outer function, you leave the inner function inside that. Okay. Now, you okay with it? All right. Now we're ready for what they call the general power rule. Okay? If that was electrical power, it'd be the general electric rule. No, we won't go there. General power rule. We've had this before, right? Now we're going to generalize it. Before we had x to the nth, right? Y is equal to x to the nth. But now we're going, instead of x, we're going to put a function inside there. So that's one of the most common types of a composite function. So the rule for differentiating is called the general power rule. To me, it's just the chain rule. Okay, I don't know why they give it a new name. What would be the derivative of this? Derivative of that? If that was it. Z in here. Derivative of z to the nth would be n times z to the n minus 1. Okay? What we do, it starts off the same one. N times u to the x to the n minus 1. Then you just do times the derivative of u to the x. U prime. Okay? So why make it a new name? Just do it. Okay? The general power rule, if y is equal to some function, u of x, raised to the nth power, where u is a differential function of x, n is any rational number. It can be positive, it can be negative. It can be decimal or a fraction. Now, it can't be irrational yet, okay? We'll get to irrationals later, but just any rational number. Then, dy dx, the derivative of this, will be first n times u of x to the n minus 1. Whatever that rational number was. Negative 3/4. Negative 3/4 minus 1 would be negative 7. Negative 7/4. But then you just got a du dx at the end, u prime at the end. Or equivalently, d by dx of u to the n is n times u to the n minus 1, which is shorthand for what they're saying here, times u prime. That's what you do. Take the whole function, inner function, n times that inner function, raised to the n minus 1, then times your u prime. All right, so let's do one. This, I hope, is example 4, yes. Okay. Find the root of this. So what we're looking for is f prime of x. You tell me. Anybody? 3 times 3x minus 2x squared times 3 minus 4x. Done. And there's nothing else you really have to do with that. If there was a common factor, you could factor it out. There's not. Okay? You can just leave it exactly like that. You don't have to square that binomial. You don't have to multiply it by that other binomial. You don't have to do any of it. That answer is perfectly fine right there. Okay? And that's how they leave it. Good for them. Okay? Let's see if we could do it on the same slide here. Yes, let u equal, now if you want to go through this, you certainly can. Okay? In fact, once you get into integration, which will be at the end of this term, we will be using u a lot more than we will integration. You can use it now if you want to, but we'll be using it later. Okay? Then f of x is equal to that thing to cubed. That was our original problem. You can just write that as u cubed. By the general power rule, the derivative is n times this thing to the n minus 1 times u prime. So why did they even introduce the u if they're not going to use it? I don't know. This would be perfectly fine if you left this whole thing out right here, because they never go back to use it. But if you want, well, they show it here. I guess that's okay. So it's 3, the exponent, times what's inside here, minus 1. 3 minus 1 is 2. Times the derivative of what's inside here. General power rule. Okay? And that's 3 times x, 3x minus 2x squared squared times derivative of the inner part, 3 minus 4x. Done. Don't need to take it any further. Don't even mess with it. That's perfectly fine. All right. So that was example 4. They're skipping 5 and 6. So let's go back and do 5 and 6. Okay. Any questions so far? Is it making sense? Okay. Find all the points on the graph. Boy, quite a different problem here. Find all the points on the graph of this function, f of x is equal to the cube root of x squared plus 1. No, that was a minus 1. You were going to let me get away with that, weren't you? X squared minus 1 squared. Okay? For which f prime of x is equal to 0, or f prime of x does not exist. After a while, I'll write that DNE. Does not exist. Okay. What would be your approach to this problem? So again, change it to what? An exponential form? Absolutely. I hate trying to take derivatives of radicals. So how would you write this as an exponential function? X squared minus 1 to the 2/3 power. Perfect, perfect, perfect. The denominator of your rational exponent is always the index of the radical, and the numerator is the power either of the radical or of what's in the radical. It doesn't matter. You can do it either place, but that is exactly it. Now that you've got that, we can now take a derivative. What would be your f? Oh, I didn't ask that. Yeah. What do we have to do next? You have to take a derivative to see where it's 0 or doesn't exist. So what's f prime of x? What would that be? Help me, help me. 2/3 of x squared minus 1 to the and 2/3 minus 1 is minus 1/3. That all? Inner part times 2x. Now that's all, okay? Now, that's a little messy to look at and probably also to try to deal with. So let's sort of get it back into the form we didn't like before, because that'll be easier to evaluate from. This 2 is in the numerator, and that 2x is in the numerator. So that's going to be 4x divided by, you got a 3 in the denominator, and you've got the cube root of x squared minus 1 in the denominator. Okay? Do all of you follow that? Okay? This is in the numerator. That's obviously in the denominator. This, because of the minus sign, is in the denominator. And if you deal with the rational exponent, that would be a cube root of that in the denominator. The 2x is in the numerator, so 2 times 2x is 4x over 3 times this. Okay, now what are the two things it's asking for? Where is that equal to 0? Now what is going to make that rational expression equal to 0? What would have to be true? For a rational expression to be equal to 0, the numerator would have to be 0, right? 0 over anything except 0 is 0, right? 0 over 7 million is 0. 0 over 0.3 is 0. 0 over anything. So where is that going to be 0? F prime is 0. That's where F prime of 0 of x is equal to 0. That would be at 4x equals 0, and at 4x equals 0, x is equal to 0. So we have one place, okay? No, this is a 4. That's not a 0. 0 over 4 is 0. 4 over 0 is undefined. But 0 over 4 is a 0. Okay, nothing, no fourths. Okay, I think in terms of a pizza. Okay, I like food, you know. So 1/4 is one piece out of the 4 pieces, right? 2/4 would be half of it. 3/4 would be 0 out of 4. I wouldn't have any. I'd be very sad. Okay, although I wouldn't have any pizza. Okay, 0 over 4 is 0. I wish that were undefined. Never. Okay, so one place where f prime is 0. Where would this not exist? What would keep something from existing? We've actually had 3 situations that cannot exist. Does anyone remember what they are? Anyone? What is something you can never do in math? And basically, Ryan was just saying one of them. You can't divide by 0, okay? So anything that would make this denominator 0, that would be a do not exist. Well, 3 of them is never 0, so that's not going to make it 0. Cube roots in general would be okay, but it's where this would be equal to 0. And where is that equal to 0? X squared minus 1. Where would that equal 0? Either at x equal plus or minus 1. Perfect. So there are 2 more places. Okay? So that's one case that you would not exist. Another is where square roots of negative numbers. We don't have any square roots. Cube roots are perfectly fine. So no problem there. It's even roots you'd have to admit. The third issue would be logs. Logs can never be negative or 0. And guess what? This hasn't got a log in it. Okay, so we found those three places. X equals 0, x equal minus 1, and x equal plus 1. Okay, so those are the values of x. Now what are they asking for? Find all the points on the graph where either the first derivative is 0 or it doesn't exist. Well, a point on a graph is going to require an ordered pair. We've got the x values. What's the y value? So f of 0, what would that be? The cube root of minus 1 squared. Right? Because if x is 0, that would be minus 1. What's minus 1 squared? Help me, somebody. Huh? 1. And what's the cube root of 1? 1. So x, so that point would be 0, 1. Okay? So f of minus 1. Now we know f prime can't be at minus 1, but there's nothing to keep f from being minus 1. So let's do f of minus 1. That's the cube root of
What's minus 1 squared? Second? 1 minus 1 squared, and what would that be? What's 1 minus 1? 0 squared is 0. Cube root of 0 is 0. So the next point would be minus 1, 0. Okay? And then we'll do f of 1. It would be the cube root of 1 squared is 1 squared is 1 minus 1 squared is 0 again. So the third point is 1, 0. Those are the 3 points. That's all they asked for. Find all the points on the graph of this for which f prime is either 0 or it doesn't exist. Okay? Now they actually graph it for you. Oh, they're going to show this. No, they're not. That's the previous problem. Okay, let me show you. Sorry, folks at home, you won't get to see it because this won't be projected. Okay, here is the graph of that function there. It's a continuous graph, but it's not smooth. That means the derivative doesn't always exist. It doesn't exist at minus 1 or 1. The first derivative does not exist there, but the function is defined there. At minus 1 it's 0, at plus 1 it's 0, and up here where the derivative is 0, at x equals 0, the value, the function value is 1, which is exactly what we found there. So there are the 3 places, goodness gracious, that's it, that we were looking for. Does that make sense? Okay? Any questions on that? All right. Let's do example 6. All right. These classes are way too long, aren't they? Okay. All right. What's that?
I think you should take a stand and let the class go early.
Oh, goodness gracious, heresy. Okay. All right. Okay. Ban him. Okay. All right. All right. We think of such a thing with it. All right. All right. Let's do example 6. Let's differentiate this one. G of t is equal to -7 over, ugly looking 7, isn't it? Okay. -7 over 2t minus 3 squared. We want to differentiate that. We want to know what g prime of t is. Now, just looking at that, what might be your first guess of how you do it? What rule? Say again? What rule would you first think of when you looked at that G of t? Yeah, you would think of the quotient rule. When you think of the quotient rule, lay down for a few minutes until you think of something else. No, I'm just sorry. Okay. Okay. Here's what I suggest. If there's a way to avoid the quotient rule, I like to do so. And I think we can by rewriting this as -7 times 2t minus 3 to the minus 2 power. And now we can use either the general power rule, don't even need a product rule, it's just a chain rule. And this is what I was saying earlier. This would make it easier to do. Okay? You want to turn that in? Good deal. Thank you. All right. Got the first paper in. Test it. I got the first paper already. Okay. All right. That's far easier to take a derivative of that using the general power rule, chain rule, than it is quotient rule. So let's do it. What would that give you? G prime of that would be I say it's easy. 14, perfect. 2t minus 3 to the second, negative 3 power. One more step. Times 2. Perfect, perfect, perfect. That can be simplified to be 28. If you want to put it back over, you can. 2t minus 3 cubed. You don't have to. You could leave it to the minus 3 power. Doesn't matter. Okay? Look at this. Second paper in. And for those who do, I hope everybody heard this when I passed out the first test. I need to see all your work. Okay? And that's why people are stapling things together, because it's really hard to get it all on that one piece of paper. Okay, good deal. Leave my lungs alone. Okay, never mind. Okay. All right. Let's see how the book did it. Example 6. 28 over 2t minus 3 to the third power. Excellent. Okay? Any questions on that? All right, simplifying derivatives. I thought we'd already talked about this, but we will talk about it some more. Okay, we just did it. The next 3 examples demonstrate techniques for simplifying the raw derivatives, or whatever that is, of functions involving products, quotients, and composites. Okay, so we're going to look at all of them: products, quotient, and product rule, quotient rule, and chain rule. Okay, example 7. That's this one. Find the derivative of that. How would you begin? You tell me. Second? Rewrite the square root? Absolutely. Okay, so I'd rewrite this first as x squared times what? 1 minus x squared to the 1/2 power. Perfect. That's the great first step. Now, where do we go from there? You tell me. Obviously, one rule's got to be done. Any ideas? It's the product of 2 terms. X squared times this. That's what the times is in there for. I mean, we say it times. Okay? It's going to be a product rule. But one part of the product rule, when you take its derivative, is also going to involve a chain rule. Okay? So, how do you eat a 5,000-pound elephant? One bite at a time. Okay? Just take it simple, one step at a time. So your f prime here will be what? What does the product rule tell you? Help me. I know it was several pages ago. Product rule. Oh, that was last section. We don't need to remember that any longer, do we? Okay, say again? Okay, she's taking derivative of the second part. Is that right? Right here? Okay, so it's 1/2. Okay, let's kind of keep them together. Not that it matters that much. 1/2 of 1 minus x squared to the help somebody, negative 1/2 power. Okay, that's the derivative of the second. You're going to have to multiply that times the first, times x squared. Oh, whoop, 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 whoop. You're going to let me get away with it, weren't you? We're not quite through with that. because that's the part that has a composite part. What else do we need? Times a negative 2x, the derivative of the inner part. Remember? Don't forget that. Okay, and this is multiplied by the first, that's the derivative of the second times the first, times x squared. Okay, that's the first part of the product rule. What's the second part of the product rule? Plus okay, you did derivative of the second times the first plus first times derivative of derivative of the first times the second. That'd be 2x times 1 minus x squared to the 1/2. Whew. All right. Now let's see what we can do with what we got. This 2 and that 2 divide out to be 1. And here we have a minus x times a x squared. So that's going to be a minus x cubed in the numerator. And in the denominator, we're going to have a square root of, well, let's see, yeah, let's do it, of 1 minus x squared. Okay? That's taking care of your first term, plus 2x times the square root of 1 minus x squared. Okay? Now, okay. You have in your denominator here, no denominator there. So to get this over the same common denominator, you would have to multiply this one by this, right? If you multiply this by this, you also multiply the numerator by that. So if you multiply this by square root of 1 minus x squared down here, you're also going to multiply it here, which squares that, right? Does that make sense? Yay or nay? Multiply numerator and denominator by the square root of 1 minus x squared. Okay? Now, this will be a minus x cubed up here over the square root of 1 minus x squared down here. And here we have a plus 2x times, and what is the square root of 1 minus x squared? Squared. The square undoes the square root, so this just becomes 1 minus x squared. Right? So let's fiddle with that numerator a little bit. That'll be a minus x cubed plus 2x, that's this times that, minus 2x cubed all over the square root of 1 minus x squared. I don't like leading off with a minus sign, so I'm going to write it as 2x minus 3x cubed over the square root of 1 minus x squared. All right. Good deal. Thank you so much. Okay. Now, to me, that's close to being as simplified as I want to mess with it. You could factor out an x out of the numerator if you don't like seeing 2 x's in there, but it doesn't really simplify anything. To me, that's a perfectly fine answer. Let's see if the book agrees. No, they factor out the x, which is fine. It's right. So you could say that's x times 2 minus 3x squared over the square root of 1 minus x squared. Okay? That's the answer they give in the book, and that is absolutely correct. The previous one is correct too. Okay? Now, notice what they don't worry about anymore. They don't worry about radicals in the denominator anymore. Why worry with it? It's not worth worrying about. Okay? So there is what we got. Any questions? Okay? I think we just barely have time to see how the book did it. So can I erase this, or you want it a little longer? Okay? So they start by writing it over. That's good. Okay? Then to take a derivative, and now they continue like we did to write that as 1 minus x squared to the 1/2. Okay? That's a much easier thing to take a derivative of. So let's take a derivative using the the product rule, and we'll use the chain rule. So it's the first term times the derivative of the second, written out in longhand, plus the second term times the derivative of the first, written out in longhand. Now let's find the derivative of that second. So the x squared times 1/2 of 1 minus x squared to the minus 1/2 times your 2 minus 2x. Chain rule part was right here. Okay? All right. That's the first part. The second part, this thing to the 1/2 power times 2x. Okay? The rest is just algebra. Okay? The 2 and the 2 divide away here. So that gives you a minus from here, x cubed from this one and that one. Okay? Because these are all things multiplied together. Times this to the minus 1/2. Okay, so that's all this term. And then your 2x they put out front here times that here. All right. Now, this is the part, I think the way I did it is a lot clearer. You may not think so. But to me, they say, factor out this thing. Well, factor out an x, because you have an x in this term and an x in that term, and this. Well, factoring this out of that is not completely obvious to me to give you that. It does, that's correct. But to me, this is no clearer than what we did. And in fact, to me, this is fuzzier, so they take it down and immediately go to that step. I think the way we did it, obviously I like the way I did it. It's, to me, a little clearer. Okay, we're not going to get to example 8 today. That's where we'll pick up next time. Let me give you a few homework exercises in this section. And actually, we got pretty far along here. Thank you. Pretty far along here. So do any of the odds 3 through 7. They're all at count chat. 3's at count view. Do any of the odds 9 through 33. They're all at count chat. 9's at count view. We didn't do the trig functions on this part, so let's stop there and we'll pick up the rest of them next time. Good deal. Good deal. Look at all these papers coming in. Super. A lot of grading for me to do this weekend when I won't be able to see, okay? Thank you so much. Okay. All right. Oh, you want something? Okay. All right. I'll be shutting this down.